So, Puxin, the screen is yours.
Right. Thanks for the kind introduction. So let me pull out my pointer.
No?
Right. So good morning or good afternoon, depending on where you are. It's a pleasure to present here on the String Pheno seminar. The topic today for me is the formulation of the weak gravity conjecture in anti-de Sitter space. And this will be based on two recent work together with Alessandro and Gary. This falls under a bigger umbrella of the swampland conjectures that has the goal of understanding some universal features of an EFT coupled to gravity that can be UV completed. Now, this picture is by no means complete. Every lotus in this picture has its own name, and the focus of today would be this one that is circled, the one named the weak gravity conjecture. Zooming into the weak gravity conjecture, since its initial proposal, it has received wide popularity and has been intensively discussed. However, it seems like the version in AdS space is somewhat limited, especially when it comes to a direct derivation from the motivation of charged black hole decay. And so a purpose of our investigation is to actually fill in this gap and to derive the AdS weak gravity conjecture bound. So let me at the very beginning throw out the punchline of the main results of our work. So the first, we want to clarify a relation between various bounds that may or may not be directly related to the weak gravity conjecture. In fact, the extremal condition for black hole has been used as an indication of a weak gravity conjecture bound. And we note that generally when there is a cosmological constant that this relation is no longer true. And we argue that the right picture for imposing the weak gravity conjecture bound is twofold. There is a condition of the charge emission of the black hole, and there is also a repulsive condition between the black hole and the particle. And these two conditions has to be simultaneously satisfied, and that gives us the weak gravity conjecture bound as motivated from extremal black hole decay. And the main result, of course, is our conjecture. It's essentially imposing a lower bound for the charge to mass ratio of the particles in the particle spectrum. This expression, ignoring the square root part, is just a result in flat space, but with a cosmological constant, we have additional contribution that modifies this lower bound that generally makes it stronger. So the rest of the talk will be divided into mainly two parts. The first, we're taking the view of bottom top. We're going to be focusing on the EFT and try to understand the black hole decay process. From this, we'll see the weak gravity conjecture bound when there is a cosmological constant. And the second part of the talk, we will try to bridge between the conjecture that we obtain with the UV. So let's begin with the bottom-up view. And here I think it makes sense to first talk about the usual story of black hole decay in flat space. We start with a black hole carrying charge and mass. In order for the space-time to be free of naked singularity, then we need to impose an extremality condition, or to require the cosmic censorship principle. This requires that the charge should be smaller than the mass parameter of this black hole. Suppose a charged particle can be produced, then we are removing some charge and mass from the black hole, resulting in a new one with a different charge to mass ratio. Of course, the charge has to be conserved, so the sum of the charges of the new objects should equal the original. Then this will provide us with, in fact, a very simple argument that kinematically, if we want the black hole, an extremal black hole that saturates the first condition to decay, we need to require that the produced particle has charge to mass ratio larger than 1 or Q larger than M. And in fact, one can realize that this is exactly the opposite of the extremality condition for the extremal black hole. We can also make the argument from a different perspective. Instead of considering the decay of black holes, we can look at how particles may coalesce and form bound states. And this will be related to a binding energy that is defined as the energy of the bound state or the combined state subtracted the original energy of the two particles. And if this binding energy is negative, it means that these particles are more inclined to form stable bound states. And this can be slightly problematic because if we continuously combine more and more particles, we'll get a state that is more and more extremal because of the negative binding energy. And at some point, this bound state will look like a black hole, more and more extremal that cannot decay. So we want to require the converse to be true, that there should exist some particles such that the self-binding energy is positive. And if we phrase this in terms of forces, in the case of Einstein-Maxwell theory, this will imply that the gauge force should be larger than the gravitational force. That forces are, the total net force is repulsive. Can we apply these two arguments in the case of AdS? In fact, there is some subtleties that arises because of the cosmological constant. One key difference is that the extremality condition, if one looks at the metric for AdS Reissner-Nordstrom solutions, the charge to mass ratio for an extremal AdS black hole asymptotically tends to 0. The relation is shown by the plot below. Mass scales roughly as charge to the 3/2 power. And so if one associates the extremality condition with the weak gravity conjecture bound, then this bound indeed will be trivialized because of this particular limit. And a second subtle point is that in AdS space, there is an effective potential, which can be roughly seen from the G0 component of the metric. The component, the potential diverges as one moves away from the center of the AdS space. And this is preventing the notion of long-range forces, since we cannot really separate particles or black holes infinitely far away. And so this signals the need to modify some of these arguments. So the natural question to ask is, should we directly associate the weak gravity conjecture bound with the black hole extremality condition? And should we directly associate the weak gravity conjecture bound with a condition of having repulsive, mostly long-range forces? The left-hand side diagram shows how the extremality condition changes with respect to the size of the black hole compared to the AdS length. And the curve above shows the result that we will derive very soon. It's the condition for Schringer effect, the charge emission to happen, and also a black hole particle repulsive condition. And we see that they separate generally. The bound we're looking for is stronger. And the right-hand side depicts a modification of what we call repulsive. And instead of talking about long-range forces between particles, we want to restore the black hole picture and instead talk about a repulsive force between the black hole and the particle when the particle is near the black hole. And this provides us with a physical picture of a black hole decay. In fact, there's two sides of this coin. The first is the quantum process of having the black hole turn into a different black hole plus a particle. This process is determined by the dynamics of the quantum fields. And there is also a classical part which corresponds to the particle eventually escaping or at least being separated from the black hole. This is the process that allows any observer to actually detect the produced particles and observe a different black hole due to the decay. And so the weak gravity conjecture should be a bound that ensures that both of these processes can happen. So in the following couple slides, we will go through the computation of the Stringer effect, the quantum process. We'll talk about the repulsiveness between the black hole and the particle, and we will also talk about how for light particles, the bound that obtained from the Stringer effect and repulsiveness can be slightly modified. The Stringer effect, it's a statement of vacuum stability. So it can be associated with an effective action when one considers the gravitational engaged field background and integrating out the charge fields. It is a vacuum-to-vacuum amplitude that is represented by the red arrow. The production rate is whatever amount of probability that the vacuum is not preserved. In other words, the sum of all the possible blue arrows. And formally, the production rate can be associated with the imaginary part of the effective action, and it represents a vacuum non-persistency. Diagrammatically, if one considers a scalar QED action or just a normal QED action, it corresponds to a summation of all possible one-loop diagrams with internal fermions or scalar propagators and arbitrary number of insertion of external gauge field legs. The general form of the production rate can be separated into two parts, a prefactor and also an exponential. Now, the computation of this production rate was discussed in the earlier paper by me and Gary. The computation is rather complicated, so here I will mostly focus on the result and the physical interpretation. I have some backup slides in case someone is interested. The exponential part can be expressed as an instanton action in the Euclidean space, which looks like trajectories. And the prefactor here is what dictates the switch-off behavior, whether the Stringer effect can take place or not. When this prefactor approaches zero, there will be a shut-off for the charge emission, and one will realize that this defines a critical value for the charge-to-mass ratio. Going through the computation, one will find this result. In AdS space, the computation is very similar with modification that gives us this R factor defined in the box over here that strengthens the bound for charge emission. And the part without the R is simply the result one would get in Minkowski and is associated to extremal, the extremality bound in the case of Minkowski. Of course, there is also the other side of this coin, that classically the particle should be able to be separated from the black hole. And in fact, this computation is a lot simpler. One can analyze this by looking at the geodesic motion of the charged particle. So what we're looking for is we want to find a distance separation of the black hole and the particle such that they can remain static in this configuration. The figure depicts the behavior of forces depending on the charge-to-mass ratio of the particle. And we can see that above a critical value, the force is repulsive near the black hole. And of course, because of the AdS attractive potential, eventually it will always win over. However, here we can identify a stable equilibrium for the particle and black hole. And when the charge-to-mass ratio drops below a critical value, then the force is always attractive and the particle can never be separated from the black hole. So if we compute the force density by looking at geodesic motion in the static coordinate, one identifies, in fact, exactly the same bound that was given before. A Minkowski part together with a correction due to the negative cosmological constant. And this bound is indicated by the upper curve in this graph. One can physically understand this strengthening as a consequence of the reduced extremality condition for the black hole. Since the charge an extremal black hole can carry in AdS generally is lower, then there is a stronger requirement on the particle side in order for the decay process to be able to happen. And one can also ask the question, what if the particle is extremely light that it approaches the IR scale of the problem? And here the IR scale is, of course, the size of the black hole. One can use the BF bound or the BF instability condition to also derive the above bound together with corrections. So if one zooms in close to the horizon, one can obtain an effective mass for particles propagating near the horizon. And near the horizon, it is well known that the extremal black hole exhibits a geometry of AdS times the spherical part. Applying the BF bound or violation of this bound in the local AdS2 space, one arrives at a similar expression, but with a correction that is significant when the Compton wavelength of the particle is comparable to the AdS length near the horizon, which is associated to the black hole size. And this will provide us with the most general form that applies for heavy and light particles. And this will be the weak gravity conjecture bound that we propose. So here I will conclude by, again, putting out the bound that we propose, that for a U1 gauge field coupled to the Einstein-Maxwell gravity, we require the existence of a particle with charge to mass ratio larger than the right-hand side lower bound. If we require that all black holes should be able to decay, we can extremize the right-hand side of the inequality, and this gives us a purely dimensional dependent quantity that appears to be 1 over this gamma that cancels the factor of just the flat space Minkowski space bound. Okay, so next I would like to move on to discuss some hints of this bound and how one can potentially look for a UV embedding of the AdS weak gravity conjecture. And this will be demonstrated by this roadmap. If we start from the EFT side and look at the Einstein-Maxwell and lambda theory, we have our original bound, but there's no guarantee that in our EFT there's actually just one U1 field. We can have multiple fields, and this will lead us to a convex Howe condition that I'll discuss. And if we try to restore the UV origin, these can come from the KK U1s due to compactification. And one can ask whether there is a tower or lattice version of this conjecture. Of course, one can also look at the supersymmetry side. And if we impose supersymmetry on the decaying object, on the black hole, these will belong to supergravity solutions. And if we forget about the UV origin, then we can generally have dilatonic black holes as a further step, a generalization of the weak gravity conjecture bound that we want to consider. Of course, if we look at the decay product and impose supersymmetry on them, then we should be looking at BPS states. And a natural question to ask is whether the bound that we obtain is consistent with supersymmetric theories. So in the following, we'll talk about the 3 roots. And mostly I'll be focusing on this green part. In other words, we're not we're being slightly agnostic about the UV nature of the generalization. So first, I'd like to talk about the convex Howe condition. If we include more than one U1 field, assuming them being minimally coupled, then we can describe the black hole and also the particles by a charge to mass ratio vector. The gray circle indicates the charge to mass ratio bound for extremal black holes in Minkowski, which also gives us the weak gravity conjecture bound in Minkowski. And as mentioned before, with a negative cosmological constant, the extremality condition for the black hole shrinks down so that charge to mass ratio of extremal black holes generally will be smaller than that in flat space. And the blue circle is the proposed AdS weak gravity conjecture bound, which in general, due to the shift of the charge to mass ratio of the black hole, is being strengthened. And to mention, this plot is we properly normalize the different charges so that here for the Minkowski case, we get a unit circle. So what then is the condition that a black hole can decay? The modification is that now we have to take a dot product between the charge to mass ratio of the particle and the direction of the charge to mass ratio of the black hole, and impose that to be larger than the R factor that we derived before. And here we define a dimensionless charge to mass ratio factor. And for multiple U1s, this will be a vector. This means that if we focus on a black hole, a specific black hole lying on this purple circle, the condition that this black hole can decay is indicated by the existence of a particle whose charge to mass ratio vector projected into the direction indicated by the purple arrow is larger than the light blue circle. If we require that all the black holes are able to decay through the collection of the particles in our spectrum, then we require that the convex hull formed by the particle in our spectrum should contain the blue circle. So the right-hand side is an example that satisfies the convex hull condition, where we have two particles combined with their antiparticles forming this rectangular shape that contains this blue circle, so that all the black holes in the theory can decay through these four particles. Generally, in the UV, then we should have a complete control of what these particle is, but at the EFT level, the condition will be given by the convex hull. So formally, the convex hull condition can be stated as follows. The generalization is simply replacing the bound on Z by the bound on the dot product of Z and the charge to mass ratio, the direction of a charged black hole. Of course, next we can consider including a dilaton, which is common consequence of string theory. This is still work in progress, but we'd like to share some of our preliminary results. The first is the observation that if we want to still compare forces, the gravitational, the gauge, and the scalar force, we need to actually look for the case where the black hole and the particle, they belong on the same spectrum. In other words, that they have the same dilaton coupling. This is the case where we have the following relation between the different conditions, that the weak gravity conjecture is given by the black hole particle repulsive condition, and generally is included in the charge emission condition. We see hints of a general form of the weak gravity conjecture, including the dilaton and also a negative cosmological constant, where this gamma factor, gamma of alpha, is given by the expression in the box, and alpha is the dilaton coupling. Without the dilaton coupling, the gamma factor is simply that of the Minkowski plus the AdS correction. With the dilaton, there are hints that it takes of this factorized form where this R now depends on not only the size of the black hole and also the dilaton coupling. The work is in progress, and we expect some results to be published pretty soon. And the final question that has been raised, I will discuss very briefly, is whether the weak gravity conjecture bound is consistent with supersymmetry. We know that in Minkowski, they're consistent because exactly at saturation value, the BPS bound overlaps with the weak gravity conjecture. we have seen that in AdS space, the weak gravity conjecture bound is stronger. So one natural question to ask is whether the BPS also becomes stronger. In fact, in AdS space, one should really talk about the conformal dimension as the energy parameter, and the BPS condition in AdS is given by charge smaller than delta. And combining that with the weak gravity conjecture bound, we identified that if the delta conformal dimension of a particle of an operator falls within this window, then indeed the two bounds, they have a non-vanishing overlap, and the theory can be consistent. Of course, we are not claiming to find an AdS origin, a UV completion of the theory, but we're just saying at the simplest check that we can do, we can confirm the consistency, and a supersymmetric theory is not ruled out by the weak gravity conjecture, which would be problematic. And that brings me to the end of the talk, and I'd like to close this talk by stating this picture. We have good evidence that the green region can be discussed, and the bound will be some generalization of what we have previously obtained. And it will be a very interesting problem if one can restore all the UV origins of these generalization and see how explicitly, for example, in a top-down construction, that indeed the AdS weak gravity conjecture is satisfied. Okay, so that's the end. Thank you for your attention.
Okay, thanks, Puxin, for your very nice talk. We have now some minutes for questions from part of the audience. Let's see. If not, maybe I can start with a quick question that I have. So, in the way that you've worked, you are considering this like a pure AdS, so it's like an actual cosmological concept. But from the bound you have obtained, I could imagine that, for example, if you start with the eta parameter in your bound, so like very small, so you have the AdS radius is much larger than the black hole radius, but somehow for some I don't know you make it large. You could have some particle that satisfied the bound at the beginning, but later it does not. Is there like something wrong with that, or would you expect something else to happen?
So theoretically, we do not know of any obstruction to taking a very large black hole in AdS. So unlike in de Sitter space, there's a cosmological horizon which prevents us from enlarging the black hole. But in AdS space, there's no such constraints. And in fact, the black hole radius can actually be larger than the AdS length scale. And so the eta parameter in the problem in our bound can actually go beyond 1. And we're not aware of any obstructions to taking large black holes like that.
No, what I mean is like you could have a small eta at the beginning, so the bound would be smaller, and then if
Yes,
it becomes larger, some of the particles that could be like sufficing the bound, then they would
right.
not. So would you expect like some other particle to take over, or that if by the process that makes that change also, I don't know, the particle mass also changes?
So we're thinking of a scenario where the particle is fixed, so the particles will not be changing charge or mass. I think the answer to that question is that when we require all possible black holes to decay, the
Okay.
requirement is to extremize the right-hand side. And that will give us the condition that we should have at least one particle satisfying the strongest condition. And this particles will have the capability of decaying all the black holes that can be constructed in just a purely Einstein-Maxwell lambda theory.
Okay. Yeah, makes sense. Thanks.
Yeah, thanks for your question.